everyone. Is okay. Can any one of you tell me if my voice is can you hear me?
Yes,
So last week we let's start this session. We have already completed till week three's lecture session material. Um, this is like course on techniques of material characterization. So last week we saw that how electron interacts with matter. We saw different types of guns, basically the material that was and how vacuum helps it, and which type of them is also being used currently, why vacuum and FEG, that is field emission ones, are useful. So after that, probably last time someone that is 11th, 12th, and that's being long. And we got a couple of overwhelming response from detailed platform that okay, we'll just go through the lectures, TA by TA and session by session. So we didn't go through this specifically, but well, since it's involved in this week's assignment, right? So you know what happens when electrons flow. So always we know that the current flow and electron flow and how electrons flow, they can be affected by both electrostatic and magnetic field, hence giving a rise to the electromagnetic field too. So currently, the microscopes which are all there, the electron microscopes work with electromagnetic field, and they have a force that's existing on them that is nothing but this. Here, this is cross. So what it exactly tells us is nothing but E times BV sine theta. It's a cross product of them. Now, when it would be maximum, when it's in the axial direction, so sine theta is zero, so it will go in along the beam of path 90 degree, so it would be 1. So again, perpendicular to it, to the motion of the magnetic field. You know, left hand rule, so the current passing and the magnetic field, so the direction of force would nothing but always be perpendicular to the path of the electron that are passing through it, which also tells us through this cross product formula. After that, there's this electromagnetic lens. So one such thing that we always should know that this lens is what we use in electron microscopes and nothing but thin lenses. And how do we define these thin lenses? These thin lenses are nothing but which are able to travel over a shorter axial distance. If their field extends to a shorter axial distance, these are nothing but EM lenses, which are thin lenses. And all the assumptions falls for these thin lenses. Again, all the assumptions fall for spherical lenses also. We only have one parameter to deal with, that's the radius of them. Now, when it's traveling parallelly, we'll only have the axial force that's exerting on them. But when it's traveling along the path, it will have a radial force also. So this radial force will exert a force on this axial force, which will eventually we'll see that axial force also exerts a component back on the radial force because it somehow travels a helical path. Now, this is that helical path that I was talking about here. So when we have an unaffected electron that's passing through the axis of the microscope or path axis, will exert this radial force. That is nothing but B rad. So this is B radial times this EV. So electron is like charge of electron is multiplied, and this is nothing but cross product with voltage of it or potential of it. Now it travels helically so that we can focus the beam or converge it to a point that we exactly want it to be. Now because of this radial force, it has this force that is nothing but on the axis of it because of the velocity of the electrons that are being deflected in this particular circumference, it will have this force that is also related to it. So hence this actual force will also eventually change it, and this helps us to focus them, so converts them, and will have a tighter and tighter radius eventually. Okay. So, as just I said that okay, how they are defined as thin lenses which are able to propagate over a shorter distance on the axis. Now, what these lenses usually are, or EM lenses, or what they have is nothing but a soft iron core. You can take this iron core as nothing but a coil or a cylinder, and across this coil and cylinder there are multiple turns of copper wire, and these are nothing but turn in a way that the difference in between each of the turn is particularly gapped so that we know that how much field we want it to be traveled through. Now, this field can only be changed with respect to the current that we are passing through it. We can change the current with respect to the current. What we have changes, we have changes in the focal length, and we can change the magnification power. Okay, so these two change things can be changed if we have the possible control over current. Okay, so this is how it looks when you have an electromagnetic lens. It's this thin, and you have the components which are lying across each other, and this is the helical path that electrons is like they follow when they are passed to the column of the microscope. Okay, that electron beam gun, everything is present over there. So now there's also a part where they'll in some cases, here, now since we have this helical path that is being traveled, because of this helical path and how many turns it will move through this helical ring, we exactly don't know if that particular ring is nothing but integral multiple. Those number of turns are integral multiple of each other or not. So because of that, if it does not end up into a even number of turns, if it sometimes end up into an odd number of turns, because of some technical issues with the lens placed with size of the aperture, sometimes our image is nothing but rotated. So because of that, some features that we want to look into the image will also get rotated. So that's why we always say that this is not a kind of distortion effect, but of course our image is otherwise unaffected, but you'll have to account for some combinations through which you can cancel out these effects. Okay. Then you have scanning coils. So why do we use the scanning coils? Now, first of all, the scanning coils are not the one which will accelerate your electrons or which will help you focus your electrons. No, not at all. These are the ones which will only help you to deflect the entire beam. So it's nothing but if you want to do something in case of scanning electron microscope, where you raster scan, is like move your beam here and there, and somehow you cover up the entire path of the specimen what you were trying to image. So this is how scanning coils help you. So if you have a secondary electron detector right here, now you want to measure that from which part of specimen it is being ejected out or being reflected back. So you scan the entire region of this. So in a way here, these coils help us. Most of the time, the work of these coils is nothing but to optimize the position of the beam in that particular column of the microscope. But they'll never converge or they'll never focus it. So it will nothing but will help you scan you through the entire specimen that you're trying to image. Of course, we know that in terms of optical microscopy, we have seen the effects of aberration. We saw chromatic, we saw the spherical aberrations, but they also exist in electron microscopes. And this problem was very evident, and people didn't start working on it till late 2010s. But till date, also, they are working on it. But aberrations is nothing but usually if you take a smaller length, of lenses or thin lens, you can easily avoid the effects of aberrations. But your lens is big enough, your focal length is big enough, your magnification is also higher, your diffraction related resolution will also be affected because aberration will start coming on. Why it affects? Why it comes? It comes due to diffraction. Why diffraction comes? Because you'll have multiple scattering across the due to the bending of the electron beam that you're passing falling through it. So if you see the spherical aberration, when we have the beam that is passing through the edges of this, when we have the beam that is passing through parallel through it, we get two particular area of intersection of our beam, that like marginal focus, axial focus. This can be at least corrected by correcting the lens, by correcting the orientation of the lens. But when you have this sorry, this cannot be corrected because you have these two passes through it. I guess both of them fall into the same criteria. Whereas also if you see for chromatic aberration, you have a blue focus, then you also have a first and third line focus over here, red focus. And there's also a region where these two also go in and lie into. So that's nothing but a disk of least confusion. So it comes into it. So how do you just correct for it? You correct for it by taking a disk of finite size. you take a disk that is thin lens, you see something which is homogeneous enough, and you can directly get rid of all of these effects, and you'll get a nothing but a monochromatic beam of light that you want, and basically all your aberrations will be reduced off from that point, so that you'll have all of your parallel rays nothing but focusing at a particular point and not having multiple focuses in it. Okay, so this is how you see in your image that okay, if aberration is there, so you'll see something rings that are parallel concentric rings which are being generated when your electron hits the specimen, and it is nothing but dissipating out and out. So only the central point is nothing but a dot in there, and above you'll see that below it, next to it, are rings that are nothing but blurred out. So that's the effect aberration causes. Somehow it relates us to de-blurring, or sorry, blurring or defocusing, something like that. So for that also people have come up with certain quantitative parameters, is like they define the amount of blur, that is nothing but this degradation of resolution caused by this particular form, where the first one is nothing but spherical aberration coefficient, second is your half angle, so that is nothing but the angle in between this beam and the angle that is traveled through it. So okay, so the electron angle in between the electron beam and the optic axis that we have, so from wherever the electrons are released, the are direct perpendicular axis, so it's nothing but the semi angle in that case. Okay, now, if you see over here, your spherical aberration coefficient, if that increases, your blur also increases. Also, if your number angle increases, so how much deviation are you giving to your electrons, so that it will be deflected back and then it will come back to your beam. Because of it also, the amount of blur also increases. Okay. So because of that, the practical way is nothing but you minimize or you restrict the electrons to the path of the optic axis or very near to the optic axis. Hence, you'll also reduce the aperture. You take a smaller objective aperture and you also reduce the semi-angle that you have over there. Okay, so all in all, we are coming to the same point that use thin lenses, use a smaller focus. If your sample is big enough or thinner enough, then it's good. You would not go into an effects of diffraction and your resolution would be okay to deal with the finer features that you have in your specimen. Now, when we talk about this resolution which is affected due to diffraction, it's nothing but net effect of both the resolutions. So eventually you'll get some terms are nothing but defined according to it. Now here what you want to see that, okay, for an electron microscope, it is defined as 0.61 lambda by beta squared that we saw previously. And here this beta is the depth of field. So that will increase rapidly if your this H value, that is our aberration or our depth of field, it also increases. Okay, it also will decrease since this value will increase. That is how it will affect. So one way, direct way to do is nothing but use a shorter focal length lens that eventually tells us that use a thinner lens. So it will have a shorter axial focus to pass through or travel through. Then we have atom interaction. So we know that electrons are nothing but they can have dual nature. This dual nature is nothing but one of a particle, second of a wave. Okay, so here what we see in electron microscopes are nothing but them as waves. It's not the particle nature of them. So these can travel coherently, can travel incoherently. When both of them, and coherent is nothing but all in one phase, incoherent are nothing but in different phases. Their phases are not equal to each other, so they lack it. So here the phase is same, here it's not. The wavelength also remains same when they are coherent. And when two coherent sources come together, you have a constructive interference at a point that is nothing but where you have maximum energy or where your focus enlarges. Wherever if they are nothing but not in phase with each other, say likely here, which are nothing but perpendicular to each other, you see something as destructive interference, which will totally give you nothing. That's nothing but zero value. Okay. So that's a simple mechanism of how interference of waves happen. Now, if you know that, then you will understand that okay, if you have, you always need an electron microscope, all waves should be coherently in phase. If they are not, then you go into an issue of aberrations. So why we need it coherent? Because we want to generate a monochromatic high energy electron beam, and that high energy electron beam, when it reaches our specimen, will only give us reflected. But this is only the energy that is reflected from the source or from the gun. What we want over here is nothing but the beam. Now how the beam comes back from the specimen also. So we cannot always say that if you have a coherent beam that's passing from the gun, this beam, when it hits the specimen, We cannot always say that the beam that we get over here is coherent. It can also be incoherent because we don't know that how our specimen will react to it, how it will knock off the electrons from it. Of course, you know the sample characteristics of it, but the characteristic beam, X-rays, everything will always depend on the atomic number of your uh, the sample that you have, nothing but the elements with their specific atomic numbers on it. Also, the energy with which the electron beam is nothing but exerted to it. So it will depend on these two factors over there. Okay. So when we come to it, we want to know that, okay, that what's the importance of this material interaction. So now it is important because of this interaction, we'll gain information into the topology, morphology, and composition of the material. So we previously saw that, okay, so these are like the two systems that are there present in IIT Kharagpur. So we see that, okay, in between these two systems, these are nothing but scanning electron and transmission electron microscopes. So they'll tell us about the elemental composition, the surface morphology. If you have a specimen that's thinner enough, then it will entirely propagate through the sample and it will give us back the electrons. So those electrons would be second backscattered electrons. But if it's nothing but a denser sample with a I guess with a lower atomic number, then in that case, you'll only have it pass because now the electrons are very located near to the nucleus. So they are very tightly binded in those cases. So if that happens, won't be able to knock out much of the electrons. So that case, what you get is nothing but the secondary electrons. Okay. So we'll see how it goes and which type of electrons are lost. But that is nothing but the mechanism of your elastic and inelastic scattering. So we'll see that. So if you see over here, you have your nucleus, and then in the nucleus you have many protons. In outside shells, you have electrons that are binded over here. Now, elastic interactions and when you assume that there is no energy transfer or no energy loss, so your sample still has the same energy, your electron still has the same energy, but in only cases your electrons are all lost. So those will nothing but eventually pass through the path, right? So it won't be there existing because beam is continuously on, so you'll get the energy from it. But no energy is transferred from the beam to the sample in this case. So it is nothing but elastic scattering. So simple case that a primary electron will lose no energy. To be accurate, a very negligible amount of energy. So what we see over here, so this is a process where it does not change any energy detectably and nothing but the electrons are scattered from the electron cloud over here if you see at an angle of theta. So again a semi-angle that is nothing but angle of scattering versus the optical axis of your microscope, and there is a charge associated with it, so amount of force also related to it. So how's that force related to it? We'll see that formula. And for inelastic scattering is it transfers some energy and then it goes and knocks off different electrons. So in this case, the energy that is caused will give you this rays, will give you secondary electrons, will pass different luminescence. So there would be different effects now that are coming through. It will all depend on the energy of the electron that are passing through the specimen and how it's interacting with your specimen. Eventually, what you see is it will nothing but heat it up. It will end up heating the sample if it is not passing through it. So in this cases, everything when it undergoes only this two type of scattering, that is coherent and incoherent. First of all, it's coherent. When it reaches the specimen, we don't know. Then what happens if it's coherent or incoherent? If it's elastic, it would be coherent. If it's inelastic, it would be incoherent. So we'll see that, okay, it's being heated up, energy is being lost over there in the process, and somehow we are getting some reflected back. Okay. So when it's an elastic interaction, as I said, we have this force, Coulombic force, that depends on the charge of both of the electrons and the distance in between the electrons in between the charges when it's scattering. And this is our dielectric constant and one constant over here. So that is how it's defined. So everything is nothing but when you have incident electrons, it will either directly pass through your sample, that is nothing but directly transmitted, or it will go back from the nucleus, will knock off and will have some backscattered electrons through here. In this case, you get a secondary electron or scattered electron, and this is your electron cloud across your nucleus. Okay, simple as that. So, if it's very a strong elastic scatter, as we see over here, to the nucleus will result in a beam of electron will pass via backscattering, and hence that is nothing but called as backscattered electrons. Okay. Now, these kind of electrons will also play a role when you are trying to see your surface topology or morphology of your sample. So they will again provide you more information in regards to the normal SEM imaging that we're doing with secondary electrons. But the only thing is your resolution would be worsened because now the electrons are coming from in depth, and the energy that they are coming bringing back to the surface has now reduced to a certain amount. So hence the resolution will also decrease in that case. But everything Justin said is like, as said, the strength of the scattering will depend on the atomic number and nothing but the atomic scattering factor and the energy that the electron beam is taking back with it. Okay. So eventually what happens, if you see this formula, uh, let's just write it here also. So if you see this formula, you see that it will nothing but these are our charges. So it will increase as the atomic number increases. So as heavier atoms will have more positive charge at the nucleus. Okay. So I take back what I said previously. You'll have as atomic number increases, the positive charge increases at the nucleus. And so this formula right here, this one, the probability of it passing through it or the beam to scatter through it here. So it's nothing but inversely proportional to the energy. So if it will get scattered if the energy is nothing but decreasing. So the probability of it will nothing but increase, right? This point right here. Okay. And then, okay, so then we also have different effects. So we also take in account the scattering cross section, that is this, the amount of path that is it traveling through. So that's nothing but your mean path free, no, mean free path length. It's something as that. It's in the next lecture, I guess. Mean free path. So it's F and then P, not this one. Mean free path. Okay, so how much it's traveling through it. So it will also depend on the cross section and the amount of wavelength or amount of distance it had traveled through. Again, we'll see that okay, if it's a single scattering, if it's multiple scattering, so how it depends on it. Okay. So these lectures are in continuation. I'll pause in for a moment and you can ask me questions. But till then, still the story is continued. I'll go on. If you have any doubts, you can unmute yourself anytime and can ask me questions. Okay. So here, as we saw the probability there, the probability of scattering the electron or how electron beam comes and the probability if it would be scattered or not. Here the probability is again dependent on the number of electrons, the scattering cross section, sigma, and the distance on it. So here nothing but the dx. How much distance it is traveling through the sample or the thickness of the sample. So you have this multiple thinner layers, right? So the distance in between this layer and this layer is nothing but dx. That is how they say, that's why they say that, okay, you need a thinner sample so that you can do its characterization much more easily and you don't lose any of the sample out there. Okay, so this interaction is nothing but we can say that it is nothing but elastic and inelastic. And there's also a case where you can always for simplistic assumption since if we assume it a sphere we'll only have one factor to deal with, that's nothing but the radius of it, so that's pi r square. And for the case of elastic scattering, this radius will depend on nothing but the atomic number, electron charge, energy, and the scattering angle. So you need to know these relationships. Don't learn them by heart, but do understand that okay how they come on. Because if you saw the previous one, the probability of interaction, it's like how much it goes through a particular sample. So that's nothing but just take a cross section and see through it. Here also, you need to know that, okay, how much radius would it have for it to occur, it's like for it to face or for it to, what they say, for it to, it's like so that it, has this elastic scattering event occurs on it, right? So then that's nothing but it's dependent on the atomic charge, it's dependent on the electron charge. So atomic charge and electron charge are the two effects that's nothing but dependent on the sample itself. And then the energy comes. So it's the energy through which it was coming and through how it was coming. So what was the path length of it? Okay. So it is stronger for heavier atoms, nothing but high Z, than for light elements. Okay. Same thing here. But now if you say that, okay, what's the total scattering cross section? That is nothing but will define by QT. So that is nothing but N sigma is equals to, we added a term of density over here. So that will get a total scattering cross section across in a unit volume. So across this unit volume of your entire specimen. Okay. So in this case also you can account for the thickness. If you just multiply by thickness for both sides, you can account for thickness also, which is nothing but given in this particular formula. Okay, so this will nothing but will give you likelihood that okay, if thickness, if scattering event will happen or not. So that is nothing but if you have rho t, that is nothing but this is your density, this is your thickness of the sample. So you have a mass thickness relationship. Okay, and then if you double this, will leave nothing but doubling of this. So just multiplied by thickness on both sides will eventually give you information about the mass thickness. So nothing but over eventually about the unit volume scattering that is happening across a cross section. Okay. And then we saw last time that okay, we do this Monte Carlo simulation. And probably that's there in this week also. But okay, so there we just see that okay, how much path two electrons travel through, and then how many scattering events are there. Based on the scattering events, these guys assume that okay, if we assume randomness in a medium, based on the randomness, how much scattering is there. Based on the scattering events, we see that okay, or we track the electron from those scattering events, and we see that okay, what's the maximum path length that the electron has been able to travel until it reaches a zero energy or until it goes back to its eventual energy, the rest energy. Okay, so here also we have just defined it and we say that okay, it interacts two times in a distance of two wavelengths. So you see, first it has been traveled through, so those are two first times, then it interacts, then it goes back, then it interacts. So in a distance of two wavelengths, you can assume this as something as relationship of nulls and in nodes and antinodes. So if you say that, okay, in a case of 2 lambda, it will scatter at two times. It's not scattering events or scattering centers, but it's nothing but scattering, the amount of scattering that's happening over there. Okay. So apart from it, it's all okay. It's all same. And then this is how your Monte Carlo simulation are something coming on. So yeah, I guess that's that only. So it forms something like this. So if you see the shape over here, the shape is called as pearl shape, or they also some people also call this pear shape, pear as fruit or pear, what you call it. Okay, so that's a drop like that, and that drop will eventually depend on the scattering cross section. So how much energy or how much area that scattering is happening through. So that will nothing but depend on our scattering cross section. If we say if this is sigma, then it will depend on d sigma by this d on rho for our, or yeah, in this case it's d rho for the amount of distance or for the amount of area it has traveled through. So in this case, that is nothing but if this is d rho for this specific sample, and then if this particular area is d sigma, then we just take ratio of them. So it tells us about the distribution and the differential cross section over there. Okay. So if we say that if this particular angle decreases, can you say what happens? So if you assume some perpendicular relationships over here, if the angle theta decreases, what will happen to your this cross section? Someone trying to say something?
The angle is increasing, you will have more intensity.
What will happen to the scattering cross section if the angle decreases? So if this angle increases, let's say if we look into a complete beam, and in that case we see that okay, the distribution of the spread of the electrons is too wide. Eventually our scattering will decrease, our cross section, this tiny bit of information that we're looking at, the cross section will also decrease. But when we are looking at a smaller surface, when we are looking at into a confined region, if our scattering angle is decreasing, if it's becoming a half cone instead of a full cone, then we'll see that this cross section will eventually increase. And because of the cross section increased, as someone just said now, intensity will increase, but that's not intensity, that's scattering. So scattering will increase. Eventually, intensity will increase if you are looking at the amplitude of it. Okay. So after that, we have something called as interaction volume. So from which part of the beam or from which shells, which type of energy do you have when electron interacts with matter? Okay, so because of that, you get something as backscatter electrons, you get something as secondary electrons, you get Agar or Auger electrons. If you say characteristic X-rays are always from the bottom, then you have some continuous X-rays also from that region and different kind of regions. Then again, after that, you have some type of, it's like first you have elastic, then you have inelastic. Through elastic scattering, you can account for structure analysis, you can account for diffraction related effects. Okay. Then you have inelastic scattering where you see where amount of energy has been lost. Okay, it is nothing but lost into your specimen and then it will reflect back. So you can get an idea about the composition of your sample. You have incoherent elastic scattering, that's also part of it. And then you have transmitted electron, which will completely transmit through your sample. And in that case, your position of your objective and your this condenser lens will totally differ. So one is on the other side, one is on the second side, and that will just observe to the second side, as in your regular optical microscope. Okay, so it's nothing but directly transmitted. So that light you'll directly see. Whereas in case of electron microscopes, or if you have secondary electron microscopes, it will reflect back to the source bin, or it will have different detectors at different angles. So which detector you try and assume to, you place that detector accordingly at that particular angle, because you know now people have been trained for the instrument and then they'll accordingly use it. So, but in this case, it's nothing but directly placed below it. So it's perpendicular to it, directly parallel to the specimen. So directly get the morphological entire information about your sample. But just in case here, for this case, your sample should be very thin, as thin as that, so that you get resolution on orders of something as zero point 0.1 nanometers, or one can directly say as something as 1 angstrom. Okay, approximately. Then you see that what happens when your atomic number increases, which is somehow possible, sometimes possible, and what happens for lower atomic numbers. How you see this pair shape drop increases in case of metals when atomic number increases. When it transfers, so energy losses happen will due to the elastic scattering, or loss will happen due to the backscattered scattering. It's not working. Backscattered scattering. Okay, so here if you see, is there something that you need to know? Okay, this is all fine. Okay, so this interaction volume, size of the interaction volume, which parameters will it depend on? Last time also perhaps we had a similar question on it. So the angle of incidence, what is this angle of incidence? It can either be alpha or beta, which angles you look at. So that's this angle of incidence. Then you have a magnitude of current. You have your accelerating voltage. You have your atomic number. Okay, atomic number of your specimen. Because of that, how energy will come. The accelerating voltage, the voltage that you're passing through, magnitude of current, because of the electrons, the magnitude of current, and hence your first is nothing but the angle of incidence. So this is how the parameters on which your depth of penetration will depend on, but also the volume of the sample, because here you have your atomic number. So if it's a high atomic number, that will also cause a different effect. So accordingly, its interaction volume would be more smaller. Okay, so here there are two parameters for this interaction volume. One is the depth of this interaction, and second is nothing but the width of the excited volume. How much this depth it is passing through it, depth of electron penetration, sorry, not reflection. That says depth of electron penetration, and then you have the width of the excited volume. This is your y. So based on these two terms, you'll be see that okay. And then people do calculate for these terms in Monte Carlo simulation. They do approximate the size of this pearl at first, and then finally they come up with values which are nothing but will reach to a resolution which will then try and mimic for different size of the electron beams that you have and guns you have, and for a specific technical parameter size of your apertures, and then they see that okay, how much penetration can it happen, and following the same how much path it is trying to follow based on the path that the electron will travel. They say that okay, if it's suitable for a thinner sample or for a thicker sample. Okay, so do you have any questions in this three sets of lecture? If not, then we'll quickly go over first two sets of lectures in week 4, and then we'll have the assignment. Any questions? Anyone? Yeah, so if not, then you can always ask question at the end of the lecture also. So we'll go to week 4 then. Week 4, first thing is like okay, sorry, I'll just try and download this first. Okay. So they have again discussed about this Monte Carlo simulation, which I think is somehow not that much related, because if you're a person not working into that area, and so just understand the basics that why people perform this Monte Carlo simulations and what's the basis for them, because apart from that, it won't be related to you anywhere else unless and until you are really into those simulations and your work really depends on them, or if you are a person who's trying to validate some experimental situations or experiments, then of course you can. And there's a KO range. This is KO not for a specific term, but it's name of two people there right there. And then we see some contrast terms over here, bright field imaging and mass thickness contrast. Okay. So we know that what Monte Carlo simulations are for is a method through which you calculate the mean free path length, the method through which you visualize the interaction volume. So, and then what it assumes is nothing but your environment has randomness into it so that you can model these terms over there. Okay, so when it assumes randomness, we no longer say that, okay, everything is coherent and your interaction volume would be well dependent on the incoherent nature of your environment also. Okay. So those interaction volumes and dependencies will again change. But just to account, because since our nature is now random, this Kanaya and Okayama, they developed a range equation, and that range equation was nothing but to account for both elastic and inelastic scattering. Now, this elastic and inelastic scattering will here give you an estimate of the interaction volume. Okay, so this range is dependent on the radius of the sphere that's centered on the beam impact point, which has at least 95% of the trajectories, how much it has traveled back. But what you should know about in here is what all factors this equation depends on. Is nothing but what all things your elastic and inelastic scattering will depend on. So first it will depend on is nothing but your atomic weight, your atomic number, your density, and the energy of your incident beam. Okay, so just in case, just you see that okay, how your atomic number increases, you see that your interaction volume is nothing but decreasing eventually. In some cases it's eventually becoming nanometer also. So that's how it's like with increasing the voltage or the energy, but increasing atomic number, your interaction volume is nothing but eventually decreasing. So here also you see that. So many great people who have performed such simulations have nothing but came upon these terms and have validated this thing so that experimentalists take it easy, and then they can just build on those parameters and go ahead with those experiments. Okay. So I guess here also they say the same thing, that it will give you the maximum distance the beam can travel in a specimen, but this distance is measured along the complex trajectory, which will help us develop because of the elastic scattering that happens over there. Okay. But they have dealt this formula to account for both elastic and inelastic scattering, and they also account for the spatial variations that are there because of the electron spread which is happening. Okay. Now, we have an interaction volume of 10. So that's nothing but a very thin transparent sample that we assume right here. So what's the effect on the atomic number? So you can have either a low atomic number or a high atomic number element, and then most electrons would either scatter in the straight path or will nothing would get deflected. Okay, so the scattering in higher angles or even backwards is unlikely in all materials. And what you'll see that the beam broadening or the likelihood of scattering into higher angles or backward will increase with higher atomic number because the energy there increases. So them to knock out will eventually will you'll need more energy. And the way you need more energy, you'll get more spread of your beam. Since you get a more spread of beam, the likelihood of the scattering event into this higher angles will also increase. So I guess I was very clear in this points and you understand this because it's just very important. Okay. And from that only, your interaction volume in TEM or SEM depends on. So as I said, but okay, it's a pear-like shape or pear-like shape, and the size of it will depend and size the interaction depth. So let's just see these two red points over here. So the first point says it increases with electron energy or the voltage. The interaction volume will increase with energy. Why so? Can someone give the analogy for the same as I did just now? Why the interaction volume will increase as your electron energy will increase or voltage will increase.
So high energy electron beam will penetrate more
Okay. And because of that,
because of that your interaction volume depth will be
will
more.
also increase. Yes, depth would be more. In second case, this depth will decrease if you have an atomic number of with atomic number of material where you have a higher scattering potential. So
Yes,
this
high
thing
atomic will have lesser depth.
exactly. So don't memorize these things. You should understand them that what's the effect due to high energy, lower energy, higher atomic number, lower atomic number. Because these things eventually remain same for cement. So you no longer need to just focus on one of the terms. It's very easy to understand them. Then you have imaging method for TEM. We have already looked at it, how beam goes through and you have different detectors for it. So this is okay. There are different imaging methods also. Yeah, this is also okay. Yeah. So there's something called as contrast generation. So why does contrast happens? When your sample interacts with your specimen, you get a contrast. From why or from where that contrast comes into play. This contrast will come if you're looking at higher magnification or if you're looking at two different scattering events. Because of that two different scattering events, your phase will change. When your phase changes, contrast happens. Okay. So because of change in phase, amplitude and or magnification, amplitude and phase contrast are likely to happen. Those kind of events will happen over there. Okay. So there are different catalysts that are there, and there are. So this is like an image that they have shown over here, but during the contraction, somehow, yeah. So when they interact, when electrons interact with the specimen, this like we have been looking at this term again and again, but the electrons will be lost due to absorption, will be scattered at very higher angle beyond the physical limit, and are even blocked by the aperture. So this is like okay, sometimes they'll be lost, sometimes they would be scattered. So a phenomenon called as attenuation. We see that okay, something is getting absorbed, getting scattered, getting reflected back. So that is nothing but interaction of electrons with the specimen, with matter that we are looking at. Okay. And then this one, last one, we'll just see it briefly so that you can do this week's assignment then. Okay. So there are two effects here also, as we have in optical microscope. We have bright field imaging, and then we have later this fluorescence imaging. But in this case, you also have something called as dark field imaging. Then you have mass thickness contrast because of the phase changes. You have some contrast due to atomic number, of course, due to higher and lower atomic number. You see higher energy, lower energy. Because of that, you'll eventually get a contrast in between within your specimen, and you have some contrast related to your diffraction. So that is basically dependent on the instrument itself. So instrument will give you contrast based on the aperture firing, giving you electron beams at different angles or nothing but passing it through the specimen. Okay, with increased energy or decreased energy will eventually also depend on the magnification that you are using over there. Okay, so here, yeah, it is saying the same thing that, okay, bright field imaging, it will directly go on the same path of the axis. So it is nothing but everything that is parallel to it. So most of the electrons are nothing but received back to the image plane. None are nothing but reflected back or detected back. So the other which are nothing but scattered back are blocked by the aperture, whereas the ones that are traveling parallelly will only go and converge to form an image. Okay, so that's bright field, how we see usually. Whereas mass contrast is nothing but if your atomic number increases, number of charge that the atom carries will also increase. If it's a heavier, that's a powerful scattering. So the Coulomb force will also increase and the contrast areas will also increase. So if one can say that what happens if the atomic number is lesser. So if we have a low atomic numbers sample, then will it appear lighter or darker?
Lighter.
Yeah, exactly. So lower atomic number samples will nothing but will appear as lighter, whereas the higher ones will appear as darker. Only because of what?
Scattering centers are less in lower atomic number material.
Exactly. So good that you all understand these things. Yes. Then we have that the thickness contrast. The contrast due to thickness in your specimen. So thick areas will nothing but appear as darker because some point electrons which are scattered into this thicker samples. So sometimes electrons which are scattered through the thicker samples will also eventually go in there, or it will need more number of energy to knock off the electrons out from there so that you get the detection back. So that those areas will appear darker, higher in mass or greater in thickness, whereas the ones which are of the same size of thickness will appear lighter in that case also. Okay, so more electrons are scattered in thicker samples than in the thin ones. So thick areas will appear darker. So this is due to thicker samples and this is due to thinner samples. Okay. Then the same relationship of the effective volume scattering cross section that we saw, that number of electrons, the scattering cross section, the density times thickness. So your mass thickness terms, which will let you have the mass thickness contrast in this terms, area and the atomic mass over here. Okay. Then it's your bright field imaging. It's elastic, so how much you want. So always remember this terms, everything has a spherical assumption. And if it does not have a spherical assumption, you'll have some terms or some constants before it. So this constant will nothing but eventually, of course, this term will remain same, but it will eventually have some inverse constants right here. So it would be function of those constants. Okay, so we'll eventually have to model it for them then. So it's always better if you have it in spherical because all microscopy related things are nothing but spherical. Your lens are also like that. They're also concave or convex and they are also thinner. So then if you don't use thicker lenses, you always use combination of multiple lenses. You don't want that thicker lenses will eventually give you more diffraction related effects. So hence people also use thinner lenses. But eventually due to multiple combination also that happens. But then they change the geometry in a way that you get through this effects or these limitations that you always see. And then there's this dark imaging. So dark field imaging, so this is a very tricky one, I would say that, okay, what we see in bright field is nothing but the scattered ones are often blocked by the aperture and they are not allowed to travel through, will directly go past through it. But in this case, those are also allowed to travel back. So they'll also pass through. So when they pass, so something is here. The objective aperture is inserted in a back focal plane of the objective lens. And if we use something like that, the transmitted electrons are passed through the aperture while all other will are nothing but blocked back. So you get this bright field image. But if we also allow the signal from the diffracted beam or the scattered beam, you also get a dark field image. So those electrons would nothing but will give you a darker region into your field. That's it, like that. So do you have any questions? If not, then we can go into the assignments. The other ones are fine. We only have one question related to this mode, but I guess you'll be able to answer that and then we'll look it into the coming week. So any questions? I can probably give you a break for 5 minutes if you want, and people who have any questions can let me know. Then we'll go to the assignment questions then. Okay, so then if not, then let's continue to the assignments then. Okay. So let me know if my screen is visible to all of you. And then we'll just go over this assignments. This week assignments are pretty okay, pretty good. So each and every week, one of us will make the questions and we try to make it as much similar to the current week's question so that you can solve them easily. Okay, so the first question, I guess it's blurred, but it's fine. The intensity of elastic scattering from a particular atom series species is maximum when the scattering angle is
0.
yes. So why?
Because maximum, the scattered beam intensity is near to optic axis.
Yeah, exactly. So the incident particles are nothing but scattered in the same direction as that of your optical axis of microscope. So it's not deflected back. So it's everything going directly into your specimen. So your explanation for the same is also here. Then next question. Electrons will lose their energy during the trajectory through the material due to which type of scattering?
Both elastic and inelastic both.
It will only
Sorry,
lose due to inelastic scattering, right?
inelastic. Sorry, it's inelastic.
Yeah.
Loss
So
of
due to
energy.
inelastic scattering, because
Yes.
elastic scattering is like no loss.
Yes.
Yes. Then this question that we just saw, the size of the interaction volume and the penetration depth of the electron will depend on what? So there are two things that depends on. First is your energy and next is your atomic number. So what happens when energy increases or decreases based on the size of interaction volume and based on penetration depth?
Increases the electron energy and decreases the number. First one.
Yes. So it will increase, the interaction volume will increase if it's passing through more energy. So it will be able to travel more deeper. Whereas the penetration depth will decrease when it is nothing but a high
Atom.
scattering potential. So with the atomic number of the material, the penetration depth will also decrease. Okay. So that is this A. Then next, here. In dark field mode of imaging in dark field mode, huh? In TEM, what happens? So due to how it's like which effect are we able to make an image? So you know that okay, zeroth order beam, everything is related to diffraction, so it won't come here. But if it's a direct beam, or if it's a direct and scattered beam, or it's only a diffracted beam, which kind of beam?
Refracted one.
Yes, diffracted one. So it's a diffracted beam because of which we get the image. Okay. Next question. In case of bright field mode of TEM, what happens? Yes, we did this. We also saw an example of this. We're using the bright field mode, so the scattered ones are blocked already, and the ones that are directly parallel to the axis are nothing but are allowed to pass through the aperture. So what will happen to the thinner or thicker samples? Yes, exactly. So the thicker samples will appear dark, and the thinner samples will have of the same material. Will be lighter then eventually. Yes. Okay. Then what will be the contrast generation due to atomic number effect? So you have two atoms over here. So first question, which is a higher atomic number, which is a lower atomic number?
Zn has higher atomic number
Yeah.
compared to Mg.
Yes. So this one has a higher atomic number. So because it has a higher atomic number, what happens?
More scattering will be
Yes.
take place, and due to
Yes.
more scattering, there will be a darker.
Exactly. Spot an answer. So the answer is B. So it will appear dark than magnesium. Okay. Next question. In TEM, the diffraction contrast is used to provide the information about what? So what it will tell us about?
Orientation of the crystal.
Sorry, someone said something?
Orientation of the crystal.
Yes, exactly. Why?
Because that angle will change, that diffraction angle.
Mhm.
Different. Suppose the orientation is different, then we'll have different results. By different.
Yes. Exactly. Okay, so in which mode of TEM the diffracted beam remains parallel to the optical axis? Is it your dark field or is it your bright field?
It's a dark field on axis.
Dark field on axis. It remains parallel to it.
Refracted beam is parallel to optic axis.
Yeah. So we want parallel, but is it off axis or on axis? You're correct about dark field, but which one?
I think one of them is that the
One of them is?
incident beam is parallel to optic axis, and another one
Yes,
is that diffracted beam is parallel to optic axis.
exactly. So in this case, the diffracted beam is parallel to the optic axis in case of this off axis dark field imaging. Why? Because in this case, we don't require any tilting. No tilting required. And why it's not required? Because the incident beam itself is tilted. Okay. So next question. You have this mode. We really didn't discuss about it, but it's something related to Rutherford scattering that we saw about the scattering constant and the effective scattering cross section. So in this case, it will provide you information about the atomic number contrast. So we'll discuss it more in the next term, next session. So what happens is, well, nothing but higher and lower, the differences in between higher atomic number and lower atomic number. So how much cross section it will travel through. So sorry, it will pass through, and based on the cross section how much energy and how much scattering of electrons is happening. So here it's nothing but or inelastic scattering, so because of that it's giving you different contrasts. So that's a mode. So we'll look on this mode, but this is nothing but a higher angle mode, so hence you get a higher effective cross section that's also increased. So because of increased cross section, your scattering will decrease but your effective cross section will increase. So that's will eventually give you information about the atomic number contrast. Okay. The next question, Which one is the inherent mechanism for any TEM specimen?
The mass
We have
thickness.
looked exactly. So we always deal with thinner samples when doing TEM, and we want them to be transparent enough also. So it's always dependent. The inherent mechanism is dependent on mass thickness contrast. Okay, so this is something to calculate. I guess we not looked into it, but here we wanted to, but it's something with based on basic geometry. We wanted to calculate what's the zone axis for 0, 0, 1 and 0, 1, 0 zonal planes. So if you know what a zonal plane is and how it goes, we'll see it. Okay. So first we just define a zone axis. How do you define a zone axis? You define it by U, V, and W. Okay. And then um, you'll have some lattice planes. Within those lattice planes, you'll have different indices. Let's assume those indices are nothing but H, K, and L. So you take different combinations of them. Highest.
Answer is C. Answer is C.
No. Okay. So we have a condition over here that if HU plus KV plus LW is equals to 0. And then if you assume in between two planes, the focal zonal planes are defined. So zone axes are defined. So let's say if you have H1, K1, L1 defined, you have something like H2, K2, L2 defined, then you just cross relate in between them. So the first U would be related by the first two terms. So you just cover up this H part, and then you have K1 cross product in between both of them. So K1, L2 minus you have K2, L1. Okay, then you have V as then you cover the in between part because that's this particular index over here. So then you have this L1 H2 minus you have L2 H1, and then you have the third one that is W. So the cover of the last one. So then you have this K. Okay, so then you have this H1 K2 minus K1 H2. Okay. So based on this, you just input this parameters right there, and so you have this H1, K1, L1, you have this H2, K2, L2, and then you get U, V, W. You can calculate them. Just right here. Indices of zone axis by focal planes. So this is first set of index, this is second set. You take cross product. Okay. So what's the answer? Anyone doing? Well, if you see, the K1 and L2 both are zeros. K2 is 1, but it's eventually multiplied with 1. So then you get this as, oh, you get this as minus 1. Do you? K2, and then you have minus K2 L1. Minus K2 L1. Oh, that's minus 1. And then you have L1 H2. L1 H2, that's 1. Am I doing it right? L1 H2 1. Oh, sorry. That's multiplied. Sorry. L1 H2 0. And then you have L2 H1. That's also 0. So this is 0. And then you have H1 K2. That's 0. Minus this times this. That is also 0. And so we just want to look at U. So what is U? This is K1 times L2. That is 0. Okay. Minus K2 times L1. So that is 1. So the answer should have been 100. I think so, but the key gives us 001. So answer according to the key is this one, which I don't know why. Okay, we'll just look in at. Anyone has an answer for it? Anyone? Okay, I guess if not, we'll just go ahead with this one. Like they did it something like this here, this part right here. It's confusing. Hmm. We'll look into it. Hmm. Now this one from Bragg's equation. So what is this Bragg's equation? The angle in between the direct and diffracted beam increases with what? So you know Bragg's equation? What is Bragg's equation about? It tells you this.
N lambda is
Lambda.
equal to 2d sine theta.
Yes, n lambda is equals to 2d sine theta. So what happens when the angle in between the direct and refracted beam increases?
So if theta increases, then d will be decreasing. In reverse means d will be decreases, and d decreases means interatomic distance will be decreases.
Then the answer is this one. We'll explain. Okay. Scattering angle of electron diffraction in comparison to X-ray diffraction is what? So it's also similar to your, if you look at the Bragg's equation, you have n lambda is 2d sine theta, and there you have effect of your diffraction related effects. But yeah, someone was saying anything?
Smaller.
Yeah, why?
The theta is very small, so sine theta is almost equivalent to theta.
Next to theta. Yes, exactly. Okay. So this KO range, that's two people's. So it depends on what? So there's a big equation for it, but we know that KO range looks on what? So then it depends on
D.
Once
which one?
D.
D. Yeah. It depends on the atomic weight, the number, density, and the electron beam energy. Okay. And last question. So you want to calculate the distance in between the atomic planes. So that is nothing but the spacing. So you can calculate this using Bragg's reflection equation. So you have this n lambda is 2d sine theta. And you can quickly calculate this if you can. So I guess the angle is also given that it's observed that 2 theta is equals to 60 degree. So you have theta is equals to 30 degree. What else information do you need? We want to calculate D from there. Wavelength you have it here. N is given as 1.
Same 0.154.
Okay. So the answer is 0.154 nanometers. Okay. That's it for this session then. The answer also comes to be like this here. Here. So that's it then. If you have any further questions, then let me
Yeah,
know.
this
Thanks for
yeah
attending.
this week 4 assignment. The last question is similar what you have discussed numerical,
Huh?
but there is I think they're missing that the 2 theta they have written is 300. Is it 300 or 30 degree?
Oh,
Can
that
you
I
check?
don't know, I guess. We'll just see.
It cannot be 300. 2
It
theta.
shouldn't be that much high, huh?
So there is some problem in
30
the
degrees.
question only. It looks
Probably.
300. 2 theta is 300.
These all are same. Oh, 2 theta is 300. But the wavelength you gave it in orders of angstrom. Our wavelength was what? 10 nanometer.
No, it's same. No, wavelength is okay, but you see the 2 theta is equal to 300. Is it 300 or 30 degree?
Should be 30 degree. I guess they messed up with the units because if you see over here, this is A naught. It's
Just
angstrom.
it is a typo. Meter means
Typo.
30 degree. Degree cannot means sometimes degree cannot be represented in format get changed.
Yeah, I guess because of that, TAs might have made any
Ma'am,
mistake.
one I have one feedback.
Yeah.
When we have to put a answer, means sometimes the required means a unit
Units.
is not given, and when we putting answer means in assignment or final assignment, it get cross means marking negative mark means not negative marking, but answer get as a wrong. So. Is it possible to means modify the question, or we should know that in which unit in question, which unit has been asked for numerical value?
Hi, yes, I guess the unit must be mentioned in the question. If it's not, then you can always mark that question and ask in the discussion forum. You can tag the TS there, and accordingly they'll have your answer rechecked. So you know this Q&A section. You can just go there, and whichever questions you feel that you have marked wrong, then you deserve marks for it. You, with respect to the amount of question and which question number, which week, you just add in there, tag the TS, and they'll answer it accordingly.
So what we should do it? We should take 30 degree or 300 degree 2 theta for
Yeah,
this
do
question.
30 degree because I think they have made mistakes. This is also angstrom, so this should be 30 degree. So this
It should
degree
not
has not
happen.
come down.
It should not happen that again they will mark wrong if I
No,
take
should
30
not happen.
degree.
Should not happen. You can say the online TS said so.
Last week's assignment also there was a formula told by teacher was different. Whatever formula is used by question is different, and that's why it is wrong. You know that beta opt. You have also shown that 0.67 lambda to the power
Yes.
1 by 4, CS to the
Yes.
power minus 1 by 4. But in the
Yes.
solving question solving,
Hmm.
it is only beta is equal to lambda to the power 1 by 4 divided by CS to the power 1 by 4. There is no constant there
Constant.
in
No.
the answer. So I don't know.
Perhaps they have not mentioned the constant there, so they assume that there's no spherical aberration effect happening.
And similarly, in one question, the relationship of this brightness with work function and temperature.
Hmm.
The professor has shown direct relation with temperature and inverse with the work function.
Work function, yes. Oh, but there's no exact formula for this.
But actually, in question they have changed. They are saying that it is t square proportional and work function is inversely proportional.
Inverse proportion.
So t square nowhere. I mean, it was told.
Nowhere it's there. Huh? It's just T. Yeah,
But
for
in the
these kind of questions, if you feel that you have been wrong, it's very easy and you can do that. People also pay attention to it, the actual TAs for it, the course TAs for it. So you can add your questions in this forum. I'm also TA for one such another course. So we do mark it, we do see. If it's correct, we do give plus marks for that particular page person. If it's a
this question
mistake
is
from the coursework side.
question is set by TAs or what?
So questions are usually set by TAs, but then they are reviewed by professors and later by NPTEL and then are only uploaded on the website.
So it seems that some disconnect is there between whatever is covered in the lecture and what type of questions are
Yeah,
marked.
perhaps it can be because these are like PhD students who do this. So
Correct. So there are some different people teaching and different people is checking questions.
yeah, exactly. So you can always tag the TAs in the discussion forum. You can request because eventually this assignments are counted for your final grades. If not
Yes, right.
to that maximum amount, but 1 mark will also help you somewhere if you want to
So,
score like have 75% more or something. So
and
you can question it.
in one of the question, two options are same.
Oh, so those kind
Two
of
are
things are
same.
fine.
So anyway, so these are
Yeah.
small things, but this numerical part again, if I take
Yeah,
2 theta is 300, then I will be
then your
marked.
answer would be messed up. Yeah.
So that looks typo error.
Yes, that is the typo. If all other questions are okay then.
All other questions are okay. Last week's assignment, all the numericals were wrong because of this unit and misunderstanding of the formula and all.
And I hope that assignment for everyone will score good marks then.
Yeah.
Okay, then thanks for attending this session. Let me know if you have any questions or else we can close up for today. Thanks for attending.
Okay, done.
Thank you. Bye.